People often say science moves in one direction, forward, cleanly, leaving old ideas behind forever. But the archive does not show that pattern, because every time physics approaches the edge of what reality allows humanity to measure, certain forbidden ideas begin to return. Not openly, not under the same names, but they return, and the deeper the models become, the harder this becomes to ignore. For over a century, modern physics presented itself as a sequence of corrections, one theory replacing another, Newton replaced by relativity, classical certainty replaced by quantum probability, old frameworks discarded as knowledge advanced. But the historical signal looks stranger than that, because many concepts considered eliminated never fully disappeared. They dissolved into newer language, new mathematics, new interpretations. The archive suggests physics did not erase forbidden ideas. It kept rebuilding them under safer names. And this pattern begins long before quantum theory. In the late 19th century, physicists believed space could not simply be empty. Light moved like a wave, and waves, according to every known model at the time, required a medium. Sound required air. Water waves required water. So what carried light across the vacuum of space? The proposed answer became known as the luminiferous ether. Today, the word itself sounds outdated, almost embarrassing, presented in textbooks as one more scientific mistake corrected by modern understanding. But that simplification hides something important. The ether was not abandoned because scientists suddenly proved space was truly empty. It was abandoned because experiments failed to detect the specific mechanical properties physicists expected the ether to have. That distinction changed everything. The Michelson-Morley experiment became one of the most famous results in physics history. Designed to detect Earth moving through the ether, it produced a near-null result, and over time, history compressed the event into a simple narrative. Ether failed, relativity succeeded, case closed. But the archive shows the transition was far less complete than people now assume, because relativity did not truly restore an empty universe. Instead, it transformed space itself into something active, flexible, dynamic. Space-time could bend, stretch, warp, carry energy, and slowly, physics began assigning properties to empty space again. The terminology changed. The behavior did not fully disappear. This is where the signal changed, because 20th century physics repeatedly returned to ideas it publicly claimed to leave behind. Quantum field theory pushed the contradiction further. According to quantum models, even a perfect vacuum is not truly empty. Particles constantly fluctuate into and out of existence. Fields exist everywhere. Every point in space contains energy activity, which created an uncomfortable philosophical problem. If nothing behaves like something, is it still nothing? Most people never notice how radical this shift actually was, because the language of physics had changed. Earlier generations imagined mechanical ether flowing through space. Modern physics describes interacting quantum fields permeating all reality. Different mathematics, different assumptions, but strangely familiar consequences. And this pattern kept repeating. Ideas rejected in one era reappeared in another under new framing. Hidden dimensions, non-locality, vacuum structure, observer-dependent reality. Concepts once considered philosophically dangerous gradually became scientifically acceptable once sufficient mathematics existed to stabilize them. The archive suggests acceptance in physics is not determined only by truth. It is also determined by language, and sometimes by timing, because scientific models do not merely describe reality. They define what researchers are permitted to imagine. At every stage of physics history, there were concepts considered too speculative, too metaphysical, too contaminated by earlier failure. And yet, many eventually returned once evidence forced the boundaries wider. This becomes especially visible in modern discussions about space-time itself. Einstein's equations describe gravity not as a force, but as geometry. Mass bends space-time. Objects follow that curvature. But newer theories increasingly suggest space-time may not be fundamental at all. Some models propose it emerges from deeper information structures. Others suggest geometry itself arises from quantum entanglement, which creates another contradiction. If space-time emerges from something deeper, Then what exactly is a vacuum? Not empty space, not classical ether, something else. Something physics still struggles to define directly. This is where the model started to break, because the closer physics moved toward unification, the more unstable the definition of nothing became. Dark energy accelerated expansion without direct visibility. Quantum fluctuations produced measurable effects. Black holes transformed information into paradox. And increasingly, reality stopped behaving like passive emptiness. Instead, the vacuum began acting more like an active system beneath observable matter. Not classical ether, but not truly empty space either. And this forced physics into a strange historical loop. Theories became more advanced. Yet some conclusions began resembling the very ideas earlier generations tried to escape. Not because science failed, but because reality refused to remain simple. By the early 21st century, another fracture appeared inside physics. Researchers had developed equations capable of predicting reality with astonishing precision. Quantum electrodynamics became one of the most accurate scientific frameworks ever created. And yet beneath the precision, deep contradictions remained unresolved. General relativity explained gravity at cosmic scales. Quantum mechanics explained subatomic behavior. But the two systems refused to fully merge. The closer physicists moved toward unification, the stranger reality became. Time behaved differently depending on gravity and velocity. Particles behaved like probabilities until measured. Entangled systems appeared connected across impossible distances. And every new layer of understanding generated another philosophical problem underneath it. This is why certain forbidden ideas kept returning. Not because researchers wanted mythology to survive, but because reality itself resisted purely mechanical interpretation. Some scientists began describing the universe as informational. Others described spacetime as emergent. Some explored holographic principles, suggesting reality itself may function more like encoded projection than physical solidity. Even simulation theory entered mainstream discussion, not as fantasy, but as a philosophical extension of computational physics. The archive suggests this transition carried an unspoken tension. Modern physics increasingly relied on concepts that earlier centuries would have considered metaphysical. Invisible fields permeating existence, probability waves collapsing through observation, space behaving like a dynamic structure, reality emerging from hidden informational layers. The terminology evolved. The discomfort remained. This created a psychological paradox inside scientific culture. The more advanced the mathematics became, the less intuitive reality appeared. Earlier civilizations imagined hidden forces beneath existence because they lacked instruments. Modern civilization began imagining hidden structures beneath existence despite possessing instruments beyond anything earlier humanity could conceive. And yet uncertainty persisted. This is where the historical pattern became impossible to ignore. Every scientific era eventually reaches a boundary where existing language becomes insufficient. Then reality begins leaking through the edges of the model. New terminology emerges. New mathematics appears. But often the underlying questions remain ancient. What is space? What is consciousness? Why does observation matter? Why does mathematics describe reality so effectively? And perhaps most importantly, why does the universe allow itself to be understood at all? The archive suggests physics may not simply be a search for external truth. It may also be a process revealing the limitations of human perception itself. Because every model humanity creates is filtered through biological intuition, sensory constraints, and linguistic structure. Humans evolved to survive environments of matter and motion, not quantum uncertainty, not relativistic space-time, not higher dimensional geometry, which means a universe may fundamentally operate in ways the human mind was never designed to visualize directly. And perhaps this explains why forbidden ideas repeatedly return. Not because older theories were entirely correct, but because reality exceeds the categories humanity keeps trying to impose upon it. This pattern extends beyond physics. Throughout scientific history, forbidden ideas often returned after technology improved enough to reinterpret old observations correctly. Meteorites were once dismissed as superstition. Continents drifting across Earth sounded impossible. Invisible germs were mocked before microscopes confirmed them. The archive does not claim abandoned theories are secretly correct, but it does reveal something more unsettling. Sometimes discarded ideas contain fragments of reality hidden inside incorrect explanations, and future science often recovers those fragments without admitting the connection openly. This is why the history of physics feels increasingly recursive. Concepts disappear, then re-emerge transformed, as if knowledge itself moves in cycles rather than straight lines. The deeper implication is difficult to avoid. Humanity may not progress by replacing false ideas with true ones. It may progress by continuously renaming approximations. Each generation inherits observations it cannot fully explain, builds models around them, then mistakes those models for reality itself, until new evidence fractures the structure again. And this creates a dangerous illusion inside scientific culture. The illusion that current language represents final understanding. But history repeatedly shows the opposite. The words change first, then the worldview changes later. Ether became spacetime. Spacetime became quantum geometry. Quantum geometry may eventually become something else entirely. And future generations may look back at modern physics the same way modern physics looked back at the 19th century. Not as foolish, not primitive, only incomplete. That assumption did not hold forever, and perhaps it never does. Because every scientific era believes it has finally removed mystery from the universe. Then reality reveals another layer underneath, another hidden structure, another contradiction, another forbidden idea waiting to return. The archive suggests the future of physics may not involve discovering entirely new truths. It may involve recognizing patterns humanity has already seen before, but misunderstood to the limitations of its own language. And if that is true, then the most dangerous assumption in science is not being wrong. It is believing the current model has finally escaped history, because the deeper the investigation becomes, the more reality begins to resemble a conversation repeated across generations. The names change, the mathematics evolves, but the same questions continue returning from the dark. Why does empty space behave like structure? Why does observation affect physical systems? Why do discarded ideas keep reappearing near the limits of knowledge? And why does every attempt to remove mystery seem to generate new forms of instead? Perhaps the archive was never documenting scientific certainty. Perhaps it was documenting the repeated failure of certainty itself. Signal stable. Archive updated. Transmission paused.